Hello, everybody, and welcome to today's lecture. I hope you're all doing okay and staying healthy. I want to start by answering some questions that I've gotten recently. The first has to do with notation. For example, if I want to succinctly express the idea of adding up the numbers, the integers 1, 2, 3, 4, and 5, I can use the familiar sigma notation right here. So I'm saying take the sum as I goes from 1 to 5 of the expression I. And here is another way of writing the same thing. So this, just to repeat, this stands for the same thing as that. Okay, people are familiar with that notation or with the similar notations for multiplication, which uses pi. But then they wonder, what do we do if we want to AND a bunch of things together? Well, for example, suppose you want to take f of 1 and f of 2 and f of 3 and so on up to f of k. How do you express that? So just invent some notation. What I do is I say, okay, take the and as I goes from 1 to k of f of I. So we just replace the sigma with and. Same thing works if you're trying to take the min. To take the min of g1, g2 up to gn, one way to write that is just by saying, okay, take the min as I goes from 1 to n of g sub I. So it's not official notation in the way that sigma and pi are, but it gets the idea across. So that's all I'm expecting from you. Now, here's another question. Here are 3 sets. And the question I want to ask about each set is, does every word in the set appear in the dictionary? So let's try it out. What about this set right here? Does every word in that set appear in the dictionary? The answer is yes. So this is true. Those things are words. Now, this set. Does every word in that set appear in the dictionary? And the answer is no. It's false because XYZ is not a word. And I'm sure that neither of those comes as a surprise to you. Then this is the question I get. What about the empty set? Does every word in the empty set appear in a dictionary? And the answer is definitely true. Every word in that set appears in the dictionary because there are no words. So yes, every word that's in the set appears in the dictionary. This question is going to come up when you're working on PS 9.3. Today's lecture comes from 2019. The previous ones you've been seeing online came from 2018. I switched because just production problems with the 2018 recordings. One thing you'll notice as we start up the lectures today is that we are repeating a little bit of what we saw at the end of the previous lecture. I'm doing that because the coverage of the increasing subsequence problem in the previous lecture was kind of rushed. At the time, I was trying to get it in right before spring break. And today's coverage expands and hopefully clarifies that algorithm.
This is where we left off last time. And so I'll just back up and repeat myself a little bit. This is longest increasing subsequence. So the idea is you're given a sequence of integers, and you're supposed to find the length of the longest subsequence in which successive elements are strictly increasing. And by subsequence, I don't mean like substring. I mean, another way to think about it is you can throw away some elements, and what you want left is a strictly increasing sequence. So what we decided was the longest increasing subsequence of this guy here. 2, 3, 6, 7. Right. 2, 3, 6, 7 or 2, 3, 6, 9. In any case, the length is 4. So the longest you can get is 4. And I can't think of a greedy solution. I can think of an exhaustive recursive solution. And that's what we looked at last time. So the key step when you're considering using dynamic programming is you've got an optimization problem, which we do. It has the overlapping sub problem property. But you can't think of a way to do a greedy choice. So at that point, you're considering just writing some recursive function that tries all the possibilities. That inevitably, that very often leads to an exponential running time. But what saves us in the case of dynamic programming? Yeah?
For future problems, we save the output at each level, and we can reuse those.
Okay. So the key in dynamic programming is, yeah, if you write the straightforward recursive brute force try all possibilities solution, you end up making an exponential number of recursive calls. But dynamic programming will pay off when you realize that most of those recursive calls are solving the same problems over and over again. So you can use dynamic programming when there are only a polynomial number of different problems to solve. And the way you do it is, when you solve one of them, you save the answer in a hash table. And next time you have to solve that problem, you just look up the answer. You have to do a complicated recursion again. So you're looking for situations where the straightforward solution would give you an exponential number of recursive calls, but there are only a few distinct recursive calls you can make. So the hardest thing about dynamic programming is often figuring out what recursive function to define, because it needs to be a recursive function that takes parameters that identify subproblems. And so this is really the key leap, deciding, we wanted to know the length of the longest subsequence. And it turns out that if we decide to find the length of the longest subsequence that starts at a given index, that gives us the subproblems we need to chew on. So let's try that out. We want to define longest of I. Okay, so let's first just get a feel for what's going on. Longest of I, we want to end up with a different number in each of these boxes. The number that goes here will tell us the length of the longest subsequence that starts with this 0. Starts with E. It starts at index 0, but it starts with the E. And then it goes and visits some of those things. And the thing that goes here will be the length of the longest subsequence that starts here. So what number has to go there? What's the length of the longest subsequence that starts at index 7? 1. Okay? And you don't even have to look at what's stored in terms of the letters. It has to be 1 because it's the last element. Now, just staring at it, since it's a small problem, you can solve by inspection. What's the length of the longest subsequence that starts at index 0? It's not so easy as longest of 7, but what you got?
B, C, F, J.
Well, start at index 0.
3.
Right, so you can go E, F, J, or E, F, E. There are a couple that are linked 3. E, H, J. Now, we already know that the longest subsequence starts at index 1, so there'd be a 4 here. Now, the reason this is the right way to describe the problem is because you can describe longest of I in terms of, let me put it this way, you can describe longest of 0 in terms of longest of 1, longest of 2, longest of 3, and so on. So you can define what goes in the first box in terms of everything that follows it to its right. So, and how many distinct subproblems are there? If you have an array of length n, how many distinct subproblems are there to solve?
N minus 1. Do you know the last one is 1?
Well, okay, we can quibble about whether plugging in 1 at the last element is solving, but yeah, there's one subproblem for every starting point. And you can describe the answer for some subproblems in terms of simpler subproblems. So the simpler subproblems are the one that are further to the right. This is the simplest subproblem, and it starts at 7. So how do you do that? How do you describe, for example, what goes in this box at index 5 in terms of what goes in the boxes to its right?
You add 1 to any box that it can attach to.
Okay, he said you add 1 to any box it can attach to. So essentially, suppose you have a subsequence that begins right here at index 5 with that F. Could the next element be J?
Yeah.
Could the next element be E?
No doubt.
Okay. So really this is the only possibility. The J is the only possible continuation. So you take this number whatever number is the longest subsequence that starts at J, add 1 to it, and that's the longest subsequence that starts at F. So let's go through the animation and see what I'm talking about. Okay, so we know that the longest subsequence that starts at E is of length 1. That's just a base case. Now, what about for J? So what I'm going to do in the animation here is, no, I didn't do it there. Let me try it again. Okay, so for index 5, the longest subsequence that starts with this F at index 5, I highlighted everything to the right to which F can attach, right? So the thing that can follow F, J works, E does not work for following F. So in terms of calculating, once I highlight in yellow the things that can follow on from index 5, how do you compute the answer that goes in a box? You take the max of all the yellow boxes and add 1. So in this case, there's just one thing. You take the max of this, which is 1, we add 1, that gives us 2. Okay, on to the next one. Okay, which of those boxes can attach onto the C, can follow on from the C? All of them. So we'll call them all yellow. And how do we decide what goes in this box? So you look at all the yellow boxes, you look at the numbers under them, you take the max of those, that's 2, and you add 1. And you get the 3. So we're defining what goes in the box in terms of what's in the boxes to the right. So what about here? What can attach onto that F? Just the J. So we take J's value, which is 1, and we add 1, we get a 2. Now what about this H? What can hook onto the H? Just the J again. So we get a 2 right there. Now, what can hook onto the B? Everything. So we take the max, which is 3, we add 1, we get our 4. And finally, the E can hook onto those 4 things. The largest of those 4 things is a 2. We add 1, we get our 3. Okay? Yeah?
In terms of complexity, how heavy would this be?
Okay.
Because it appears that the worst case scenario is you'd be looking at both sets A and longest set continuously while they grow up until you reach
Okay. So what was the complexity of filling in this table right here?
constant.
Well, it's not constant. Is it linear?
How do you find the yellow ones?
Okay. So what work do I have to do? So let's say I'm trying to decide what goes in box 2 here. I've got to scan everything to the right to see what can follow on from this H. And then I've got to potentially scan every number to the right and find their max. Sometimes I don't have to look at every number. I gotta look at some of them. In worst case, I look at all of them. In any case, I have to do something for every index to the right of the one I'm working on. So I have to scan nothing to my right for this. I've got to scan 1 thing to my right to do this one. I've got to scan 2 things, 3 things, 4 things, 5 things, 6 things, 7 things. This doubly nested loop. So what's the complexity? It's n squared. So it's an n squared algorithm. So this is traditional dynamic programming. Traditional dynamic programming is you've got some problem you want to solve, you turn it into the problem of systematically filling in a table of solutions until you get the solution that you want. Okay? Now, it can be hard to visualize filling in a table sometimes, which is why there's another approach that you can use as well, the approach we used last time. So you've sort of got your choice of dynamic programming. Either build up a table that can hold the answer to each subproblem, and then systematically fill it in this case from right to left. Or, what's the alternative? What was the alternative we saw last time? Yeah.
Has partial solutions in its parameters and like a recursive stack.
Well, yeah, what we did was we wrote a recursive algorithm to do this. But then how do we make it efficient? There's a trick to making the recursive algorithm efficient.
We have that dictionary.
Right, we added a cache. So basically, rather than constructing, say, an array and filling it in systematically, we just created a cache and filled it in whatever order the recursion cared to fill it in. But the cache would end up holding these same values. So dynamic programming got its name before programming meant what it does today. Dynamic programming referred to the task of figuring out what table to use and filling in the table. Nowadays, you hear dynamic programming, your first thought is, binary search trees or something, some dynamic data structure, but it's not. Now, up here is sort of a mathematical description of what I did. I said longest of I depends on the max of the things that, this is saying, look at the indexes that are bigger than I, and find the max of either longest of j, if j is something that can hook onto I, or 0, and then add 1. So this just summarizes what we're doing down here. So it tells you, find the max for every index between I and n of this expression right here. So that's traditional dynamic programming that someone from the 50s, say, would recognize as dynamic programming. Now, this is often an easier way to do it. So here's the direct recursive computation. So we want to find the longest increasing subsequence of an array. And so what we do is what are we doing in that loop right there? So this loop right here. In fact, let me come back to that. This is what we, let's focus on this one. This is what solves our subproblem. So longest subsequence given an array and an index I. So this method here finds the length of the longest increasing subsequence that starts at index I. So what's happening in this loop?
Finding the max in an index that's higher than I.
Yeah, we're starting j at I plus 1. We're going all the way to the end of the array. And then for each element, if a sub I is less than a sub j, in other words, if a sub j is something that can extend a sub I, then we found a new, we're looking for the longest path that starts at some index to the right of I that's compatible with I. So it's just an optimization loop that solves the subproblem at j and sees if it's bigger than the largest length that we've seen so far. It's just looking at all the numbers to the right, figuring out the largest, as long as they're colored yellow. And then once we found it, we add 1 and return our answer. This is just doing what I did by hand. Or another way to put it, this is just an implementation of, okay. For some reason, that loop is just an implementation of this summation right here. Okay? My PowerPoint has screwed up where I can't go backwards, but so I'm going to do this. So this is what we've been talking about the last 15 minutes. This just automates that process. So what's this up here? Yeah?
Starting from the end, finding the longest subsequence, so that at the end it would be just 0.
Right. So the last step, once you've figured out the length of the longest subsequence that starts at each index, we would have to go find out which is the largest. And that's our overall answer. That's what that does. It just goes through and figures out, okay, which of these subproblems gives us the biggest answer and returns it. Yeah?
Wouldn't it be the same thing if we try to find the longest subsequence using the second method and just start at index 0?
Okay. Okay, so what if we ask for the longest subsequence that starts at index 0? What would we get back as our answer?
The same thing that started from
Well, we would get back 3. We already know that. So if we just ask, what's the longest increasing subsequence that starts at index 0? The answer for that example was 3. But what is the longest increasing subsequence in the array? 4. It's the one that starts at index 1. So that's why this method has to basically solve, it computes longest SS of max length of n minus 1, a dot length minus 1. So it basically looks at the longest increasing subsequence of each at each index and returns the longest of those. Yeah.
For the top one, when you recursively call it, should it have I in it? Because it looks like it only has one argument.
Well, this is the recursive call right here.
Yeah, it's a comma I, but then when you define it, there's only one argument.
Oh, I overloaded it.
Oh, okay.
So this is calling this down.
Oh,
Now, what would happen if we put that in there, put that into a program, create an array of length 1,000 and let it go?
You just have 1,000 squared.
What's that?
You just have the possibility of 1,000 squared iterations.
Well, that would be nice if you only had to do 1,000 squared iterations. That would only be 1,000,000. But in fact, what would really happen? Yeah? It would, yeah, it would be exponential. It would never finish in your lifetime for a 1,000 element array, because it would just be making all kinds of recursive calls. How many distinct subproblems are there for a 1,000 element array? Well, no. How many distinct subproblems? There are exactly 1,000 subproblems. You would end up solving some over and over and over again. Like to compute the longest subsequence at index 10, you'd have to compute the longest subsequence at index 11, 12, 13, 14, and 15. Well, when you computed 11, you'd be computing 12, 13, 14. When you computed, we saw this last time. It just blows up. So how do you make this efficient?
Make it with a dynamic programming problem.
Right, you just, either you say, this is dynamic programming, so I'm just going to fill in that, I'm going to create that array and fill it in systematically like I did when I did the demo. Or, how can you, without thinking too hard, take this recursive solution and make it n squared instead of exponential?
Create a cache.
With a cache. That's all you have to do. So, this is the first method I gave you. We just create a cache, a hash table, and we pass it to the other recursive method, to the method we really care about. Okay? And this cache maps ints to ints. What are the two ints? What are the keys? Indexes. The keys are those things. And what are the values? The length of the longest subsequence that starts at that index. So that's to hold, as we solve subproblems, we're going to store the answer in the array, in the cache. So this is what we do. This is our code from before, except we've got to pass the cache along each time I make a recursive call. When I enter, I look and see, have I already computed the answer for index I? If so, return it. When I'm done, I take the answer and store it in the cache before I return it. That means the next time someone needs to know the solution to a subproblem, we've already computed it. So it takes what would be an exponential algorithm and turns it into an n squared algorithm. Makes a huge difference. It is really easy. And so when you solve your caddis problem, what I suggest you do is, you solve problem 9.3. It basically shows you how to write the recursive method that needs to be written. Write the recursive method. Forget about caching. Just write it. Run it on caddis. What will happen? Probably. It'll time out. In fact, what will happen is it'll pass every single test except the last one when it'll time out, probably. Okay? Now, at that point, you've accomplished. What have you accomplished? What's that?
Most of the problem.
You understand the problem. You have verified. If it gets to the last test case, your recursive implementation is probably correct. It's just too slow. First step is to get it so that it at least passes every test except the last one. Then, what can you do? You just slap this sort of code at the beginning and the end. And then bam. I watched it happen yesterday at my office, so I know it works. Okay? Now, alternatively, you could write it completely different. I don't know if I have it. No, I don't have that one. But you can imagine writing a loop that declared an array and then a doubly nested loop that filled in the array with the answers. like I demoed. You could write it that way. That's traditional dynamic programming using a table. This is sort of a simpler way to do dynamic programming using a cache. And there's some trade-offs. Sometimes one is better than the other, but for many cases, either is equally good. So, don't get caught up on the cache. The cache is supposed to be the trivial part, just for saving the answer. The part that we have to expend some intellectual energy is figuring out the recursive solution in the first place. So that just takes looking at lots of examples. So let's take a break and then we'll look at this example. Okay, so this is a classic dynamic programming problem. So the problem is we're given two strings, R and S, and we want to find the smallest number of edits that will transform R into S. And what you're able to do is you can delete a letter from R, insert a letter into R, or replace a letter in R with a different letter. So think of the edits are happening to R, and the goal is to turn R into S. So can you think of some applications for this, for a solution to this problem? Where do you care about the minimum edit distance between two strings? Yeah?
Autocorrect.
Okay, all right. See, like autocorrect when you're texting, right? You type some word that's not quite a word that suggests something close to it. Or spell checking is another example. You misspell a word, you want to know the similar one. Yeah.
This is kind of oblique, but if you had like a loop already, then trying to solve the traveling salesman problem could be done with a similar approach.
Okay, so right, that is oblique.
But I mean, like,
Yeah.
you can kind of see what I mean by that.
Yeah.
I'm assuming.
Yeah. Okay. I've used it for to compare programs before. To see, you know, here's two programs. What is the edit distance? How much do you have to change this program to obtain this other program? I've used it to try to detect cheating. The problem is the edits that you do when you're creating a program aren't necessarily this kind of edit. It might be copy this chunk and paste it in. So you have to change the definition of edit. Okay? Can you think of an example in biology, an application in biology? Right. You take a couple of DNA sequences and you want to know how similar are they. What are the edits in that case? Yeah, so someone answered that knows more about biology than me. But essentially, mutations are your edits. You know, over time, the DNA sequences change as species evolve, and you can tell which species are closer together by just looking at how close, you know, what's the relationship between their sequences, and what mutations have occurred over time. How many mutations does it take to turn one sequence into another? So it has its applications. So let's look at an example. So let's say we start with snowy and we want to turn it into sunny. How many edits does it take? What's the minimum number of edits to turn snowy into sunny?
3.
Okay, I've got votes for 3. Anyone see a way to do it with 2?
With the end to where the W is, and
Okay, do what?
with the end to where the W is. And then,
So replace the W with an N?
well, I don't like, yeah, you have to do 3 edits, but you can.
Right, so if you were allowed to sort of move this on top of the W, that would, but unfortunately that's that's not one of our editing operations. So yeah, using the edits, the operations we have available, it's 3. And there are various ways to do it. Imagine I have one here. We can insert a U at the right place. Maybe stick a U right after the S. And then replace the O with an N and delete the W. That gives us from snowy to sunny. Now, that's not so hard when they're 5 letters long, but imagine if it was 1,000,000 letters long and you want to know what the distance is. Can you think of a situation where you have 2 million element strings, 2 million character strings? They differ, every pair of characters differs, but the edit distance is like 2. What would that look like? Yeah?
2 strings that are basically the same, but one of them has an A at the beginning.
Okay, so 2 strings that are the same, except they start out the same, but you take one of them and you stick a letter at the beginning and lop off the last letter. Now everything's shifted over by 1. and everything is screwed up. But it's just an edit distance of 2. You just, to get back, you just delete the letter at the beginning and then stick the correct letter at the end, and now they line up. Okay. You know, you can always ask, can you think of a greedy solution? And the key thing, you're asking, can you think of a greedy solution? Sometimes these problems are known to be difficult, NP hard, which we'll define in a few weeks. And it's extremely unlikely there's a greedy solution. Other times, it may be that maybe there is a greedy solution, but it's no more efficient than dynamic programming. But in this case, I don't know of a greedy solution that works any better than dynamic programming. And this is the approach we're going to take. We're going to focus on we got to define the subproblems we care about. And so the subproblem is going to be, they're going to come out by focusing on the last character. So let me show you what I mean. We're going to define the distance between n and m to be the minimum edit distance between the first n characters of R and the first n characters of S. So there's our subproblem. Okay? So R and S are sort of implicit parameters to this thing, just to keep the notation simple. And so the subproblems we're going to solve are all the form making the first n characters of one string the same as the first n characters of another string. So how many subproblems are there? How many distinct subproblems are there if, and now I'm going to change notation, if one string is of length n and the other string is of length m? How many distinct subproblems are there? N times n. All pairs of valid substring lengths. Okay, so that's good. It's just quadratic number of subproblems. All right, so let's look at this. Suppose that you are trying to find a way to turn string R into string S, or at least this is the part of the string. This is the first n characters of one string. This is the first m characters of the other string. And you got to convert one into the R into S. Okay? How would you do it in this case? How would you define the problem of turning R into S in this case where the last characters are the same? What's the minimum edit distance in that case? Can you define recursively the minimum edit distance between R and S in case 1 there? Where the last characters agree.
I'd say 5.
You'd say 5. Well, we can't say, the answer isn't any given number because we don't know what those yellow question mark characters are. So we got to define, E of n and n is the minimum edit distance between the first n characters of R and the first n characters of S. So we need to define this in terms of E. How can we describe the solution to this problem in terms of a simpler subproblem? How can you take advantage of the fact that they end with the same character? Yeah.
Is it just that you know that they have the same character, so you can
Well, if you
pretty
know,
much
if you,
and split it into a smaller problem?
well, right, we know that the last two characters are the same. So what subproblem can we reduce it to?
All of the other ones.
We got to find a way to convert these remaining characters into those remaining characters. Okay, so it looks like this. In this case, if the two strings R and S end with the same character, the edit, if the first n characters of R and the first m characters of S end with the same letter, then the edit distance n comma m is equal to the edit distance of n minus 1, m minus 1. In other words, the cost of turning this string to that string is the same as turning those 5 characters into those 3 characters. You can lop off the A's, they match, and focus on what's left. So this is a recursive definition. When the two substrings end with the same letter, you just define the edit distance of the longer strings in terms of the edit distance of the shorter strings. Now, what about the case where they don't end in the same letter? There are 3 possibilities. We can replace A with a B, we got to do something with this A to make it match up with this B down here. One thing we can do is replace the A with a B. Another thing we can do is just delete the A. Another thing we could do is insert a B at the end to match that B. So we're going to come up with a recursive definition for E of n comma n in all these cases. So what is the edit distance between R and S when they end in different characters and you decide to replace the last character of R with something that matches the last character of S? Yeah.
Is it just case 1 plus 1 for the replace?
Exactly. It's just this. Okay, so what I do is I convert, basically, essentially, I replace the last character of R with an A, and there's our formula. The edit distance between these two strings, between these two substrings, is one more than the edit distance between those two substrings. Because we do one edit to make them agree in the last letter, then we scratch off the B's, and we got to turn those 3 yellow question marks into those 5 yellow question marks. So we reduced it to computing the answer to one subproblem and adding one to it. Okay? What about in the case we do a deletion? So we decide, okay, we got a problem. Our 2 substrings end with different letters, so I'm going to delete the last letter of R. And then go from there. What would E of NM be in this case? We've done one edit, right? The deletion, plus, what strings are we converting now? It's not exact, it's not the same as this. Yeah?
Would it be 1 plus E of n minus 1 and m?
Yes. Okay? It's 1 plus E of n minus 1 and m. Why n minus 1? Well, because we turned that A into a B. We deleted the A and got rid of it. So we're left with fewer characters. That's the n minus 1. We didn't, we still got to worry about that B on negative S. So we reduced the problem of matching R and S to the problem of matching a slightly shorter version of R to the original S. And what about the case where we decide to do an insertion? In other words, we just decide, okay, another way to deal with that B that's sitting down in S is to stick a B on the end of R. Then we can sort of, okay, the B's match and then turn this string with the 3 question marks into that string with the question marks including the A. What's that going to look like? Yeah?
1 plus n and n minus 1.
Okay? So it's sort of the flip of that. So it's E of n. We still got to consider all of the original R's, but we ignore one of the characters in S. Yeah?
Why is it that we add or insert B in front of A instead of replacing it with B?
Well, we consider that over here. They're only, you've got all the edits apply to R. We've got to edit R in some way so that the last character of R matches the last character of S. And there are only 3 ways to do that. We can replace the last character of R with something that matches this B. We can delete the last character of R and hope that gets it to a good situation, or we can do an insertion. There's only 3 ways to deal with this B at the end of S. Which is best? How do we know which is best? Which of these 3 should we do? Okay. I have a replace and I have a depends. Yeah?
It depends on the relative lengths of R and S.
Well, it depends on relative lengths of R and S. It depends on what letters are in R and S. So how do you decide? Yeah.
I would assume we're optimizing for whichever one has the smallest distance between the 2. So we just have to try them, I guess.
Right. Now, if there were a way to make a greedy choice, we would. So a greedy algorithm would say, I can either do a replace, a delete, or insert. And it would do a quick calculation. Replace this time. And then it would have a simpler subproblem to solve. Then it would say, okay, this time insert. This time delete. We don't have that. So what we do is we try all 3. See which gives us the better answer, and add 1 for the edit. So if the 2 strings agree in their last character, we're in luck. We reduced the subproblem to the original subproblem to a simpler subproblem. So, we haven't expanded the recursion tree. It's just one-to-one. But if they ended with different characters, we've got three possible edits. We try all three. We make 3 recursive calls. We figure out which gave us the shortest answer back, and we add 1 for our edit, and that's our answer. Okay? What's going to happen though when you take these long strings that you're trying to match, and they disagree on their last character, you make 3 recursive calls.
Just exponentially.
Right. You suddenly got exponential growth. You're getting, at worst case, you're getting 3 recursive calls at each level of the tree, or each node of the tree. It just blows up. But they're only n times m, the length of r times length of s, distinct subproblems. So it's ripe for dynamic programming. Okay. So E of 0, 0, let's try to write this recursively. I know I've used brackets, square brackets, it looks like array. Why does this make sense? This is saying that to convert the first 0 characters of R into the first 0 characters of S takes 0 edits. Does that make sense? Okay. What's that saying?
First 0 hits R to n.
Okay, so converting an empty string into a string that has m characters is going to take m insertions, right? And that's saying to get from an n character string to an empty string, you got to do n deletions. Okay, so those are base cases. Okay, that case is a situation where you've got a substring of length m and a substring of length m, and they agree on their last character. And from the previous slide, we just know that reduces to this subproblem. Okay, and then these are the other 3 cases. In the situation where the 2 substrings don't agree on their last character, we try all 3 of these possibilities, find the smaller of them, add 1, and that's our answer. So that's the recursive solution. Okay, how would you implement this? At this point, we've done the heavy lifting. We've done the creative work. It ought to be a straightforward coding problem now to do this. And I can think of, there are 2 ways to do it. We can build a table, we can do a recursion. How would you do a recursion?
Write out your base cases and
You turn this, it's almost a Python program already. You just write a method that takes in the E that takes in these 2 parameters, and it says, okay, if they're both 0, return 0. If the first one is 0, return the second one. If the second one is 0, return the first one. If they agree on their last character, make a recursive call. If they don't, make 3 recursive calls, take the mean, add 1. Return the result. That's easy to turn into a program. And you run it, and what'll happen?
You done?
Yeah. You literally, you die before your program finishes. If the string is So, how do you make it so you live to see the answer to your question?
Write a decorator function, since apparently this is a Python program now.
Okay, so you're saying you could,
You can write a function and you just put at the function name, and then it caches everything you put into it. It's great.
okay, all right. So apparently it's super easy to do caching in Python. I didn't know that.
I love it.
Okay? Basically, you use our caching trick, and suddenly it's just a quadratic problem instead of exponential. Or you could take a clue from, or not a clue, a cue from my array notation here, and think of the problem this way. You could think of the problem as, you could think of this stuff here, this notation, as directions for filling in that array. So those are, if we're converting snowy into sunny, that 2-dimensional array is meant to represent every possible solution to every possible subproblem, right? Because each subproblem is going to involve either the first 0, 1, 2, 3, 4, or 5 characters of snowy, and the first 0, 1, 2, 3, 4, 5 first characters of sunny. So that's 6 indexes, 6 indexes. So there are only 36 subproblems. And so we can create this two-dimensional array and store the answer to each subproblem in those boxes. And the trick is to store them in the right order. You want to store them so that at the point where you need to know the answer to a subproblem, it's already been stored into the array. With caching, you don't have to worry about doing things in the right order. You just fire off the program and it naturally caches things as it computes them. What's the right order for filling in this table? Yeah. Well, what happens if we start, on what values does that top right corner depend on? It depends on the one to its left, the one diagonally to its, below to its left, and the one below it. So we don't want to start with the upper right corner because we won't have computed these squares that it depends on before we need to compute it. And we start in the bottom left and work to the upper right. Now, where will the final answer be written? Which is, I think, the answer question you were answering. Top right is where we'll find the overall answer for the minimum edits to convert sunny into snowy, or snowy into sunny. Because that's the box that will contain the minimum edit distance from the first 5 characters of snowy to the first 5 characters of sunny. It will be in that upper right-hand box. Now, if we just wrote it recursively and fired it off, it would fill in a cache with 36 values, and the answer would be in the cache. Or we could write a doubly nested loop to fill in the array. But doing that takes a little more cleverness because you got to figure out the right order to do it in. So let's, why did I put a 0 there? So I'm starting at the lower left. How did I know to put a 0 in that box?
It says it right there.
Says it right here, right. Think of E as a two-dimensional array. Instead of thinking this as recursive calls now, just think of it as array expressions. This says E of 0, 0 is 0, so I put it there. Let's fill out the rest of this row. How do I know what to write in this row here?
Because it says it right there.
Because it says it right here. Okay, if the first one is, well, which ones does it say it in? See, these are the N's and those are the M's. So this says if the second one is 0, in other words, M is 0, then you store N's value. So, make a long story short, we fill all those in. What else can we fill in without thinking too hard? This column here works the same way. That's the other base case. So I just filled in using the base case. This says put 0 in the lower left corner, then store N's along this one, and store M's up there. Okay? So that's just easy. Now we're going to take the strategy of we're going to fill in this box, this box, this box, this box, this box, and then the next row, and on and on and on until we get to the top. Now at any given time, like take this square right here for example, which ones does it depend on? According to this formula right here. So when you're deciding what to put in this, let's say this box right here. Let me go one step further in the animation. Okay, let's say you're trying to put what's in this box here. What three numbers do you have to look at when you're deciding what to put in that box right there? Yeah.
The one to the left, is it the one at the bottom left?
Right, the one to the left, the one below it, and the one diagonally down. Because that's just what it says here. This says that's the one to the left, that's the one below, that's the one diagonally below. Okay? Now, that's if the case where the characters don't agree. What about in this case right here, this yellow case, which is a case where N and N are the same? How do you decide what to put in that box? In that case, we're in this situation here, where the two letters at the end of the substring agree, so we just look diagonally down to get our number. So what I've done is I just highlighted in yellow the places where the last letters in the substrings agree, so I won't forget when I'm doing the animation. So I made this one yellow because both strings start with S. Okay? Those two are N's because are yellow because this is an N, and those two rows are an N, and same for the Y. Let's just so we won't forget which case we're in. So let's start filling it in. How do we decide what goes right there in that box at 1, 1? Okay, we're at a case where the characters agree, so we just look lower, diagonally down, and copy that number up. 0. How do we decide what goes in this box right here? N is 2, M is 1. We look at the three neighbors. We take the smaller, we add 1. So 0 is the smaller, we add 1. So we get a 1 right there. Okay, now we're here. We just look at the three neighbors, take the smaller, add 1. We get 2. We get 3, we get 4. Okay? Now we're back over on this row. How do we decide what to write in that box? We're just doing array calculation. We look at these three numbers, we take the smaller, we add 1. We take the three numbers, we add 1. 2, 3, 4. Okay? What do we write here? Right? 3, 2, and 1, the smaller is 1. We add. Now we're in a case, we're not in the triply recursive case, we're in the singly recursive case, so how do we decide what to write here? You just copy the thing diagonally down to the left. So there's no recursion involved here. It's just a doubly nested loop that's just going through and filling in according to this very simple rule. So we get a 2, we get a 3, we get a 4. Up here, the min is 2, so we get a 3. Here, it's just a diagonal copy, 2. This will be a 2, a 3, a 4. And now finally up here, 3, 4, 5, we get a 4. 2, 3, 4, we get a 3. 2, 2, 2, we get a 3. 3, 2, 3, we get a 3. And then this box, how does it get its number? Just diagonally down. Okay? Well, that's just a straightforward loop fill in the table. Or you could write it recursively and fill in a cache. Either way, you get the answer. So, which of these slides was the hard part? Yeah, that slide where we were considering, okay, we're coming up with recursive definitions in the case where we replace, insert, delete. That's the tricky part. Once you get past there, this is easy. After I ended class last time, at least 2 people came up and asked me, well, what's the answer? Where do you find the answer to the overall problem of turning snowy into sunny? So where is the answer? How do you extract the answer to the original problem from this? Yeah?
It's the number in the top right column.
Right, it's the number in the top right column. That number tells us the minimum number of edits it takes to turn the first 5 letters of snowy into the first 5 letters of sunny, which is to say all of both strings. Now, we talked about the optimal substructure property. And you can see the optimal substructure property exhibited here, in that the solution to every subproblem is in that array as well. So what's the minimum number of edits it takes to convert the first 2 characters of snowy into the first 3 characters of sunny? Right, you just come here, come up here, that's 1. So you can read the answer to any of the problems out there. So that's basically where we stood at the end of class last time. So let me pause and see if there are any questions about this before going on. Okay, now, suppose you had to code it up. There are 2 ways you can do it. You can correspond to what I just said a minute ago. You can view this as a recursive function definition, or you can view it as array update operations. So let's look. Here's a direct recursive computation. So we want a method that takes in 2 strings, R and S, and computes the minimum edit distance. So I'm going to make use of this helper here, min edit distance, that takes 4 parameters, R and the number of characters of R we care about, and S and the number of characters of S we care about. And initially we care about all of them. And here is that helper function. And look at it, what do you see? Where have you seen that before? Yeah.
That's the same set of instructions we filled the array out with.
Right. That's just the, it's this. It's this stuff here. The only difference is I only have 2 base cases because really this base case is a special case of both of those. But these two base cases, these two recursive cases. I just carried it forward into the implementation. The two base cases, the two recursive cases. This simple one applies when the characters agree. This three recursive calls applies when the characters don't agree. So it's just a direct implementation of that thing. So once you do what we did on the other slide, this just falls out of it. Now, what's going to happen when we run this on sizable strings? Suppose we ran it on two strings of length 1,000 that have no characters in common. Okay, what's going to happen? Yeah. It's gonna. You start with you got the problem. You got to solve the problem when when you care about the first 1,000 characters of both strings. That'll make 3 recursive calls to the 999 level. Those will they each make 3 recursive calls. Those will all make 3 recursive calls. So it's a disaster. But that's easy to fix as well. You just create a cache. So to the I add another parameter to min-edit distance, which is the cache we're going to use. It's a dictionary that maps pairs to ints. Now, why do we want to have pairs as the keys and ints as the value of this cache? Yeah. Okay, so the parameters there are 4 parameters to the method that we're going to cache. 2 of them don't change. R and S are always the same, so we don't need to worry about them. The parameters and values change each time a recursive call is made are this parameter here and this parameter here, which we're using as array indexes. And so it's the pair of them that define the subproblem. So we're going to map unique pairs of this parameter and that parameter to the minimum edit distance that corresponds to it. So we create the cache, and then we change our other method this way. We add the parameter. When we first enter the method, we look up the answer, see if we have the answer saved. If we do, we just return it. Otherwise, when we compute an answer, we cache it, and then we return the cached answer. So it's just pretty simple change to the existing method, really a mechanical change to the existing method. And it makes all the difference. Suddenly, now the complexity is going to be the product of the length of the 2 strings. So both strings are length n, and we got an n-squared algorithm. Okay? So, there are degrees of misunderstanding you can have about this. You can be uneasy about where this came from. Okay? You could understand this and not understand that, which would actually be worrisome. I mean, not understanding that's very understandable. Once you see that, seeing that this is really just a direct implementation, that's pretty straightforward. And this part of adding the cache is just purely mechanical. So that's why I keep saying the creative part was coming up with that original idea of defining minimum edges in a particular way and coming up with the recursions. The rest is just mechanical implementation. All right? Now, what would it... I mentioned that you can also view the problem not as making recursive calls, but as just filling in the array the way I did in that animation. What would that code look like? What if you wanted to code it that way? Start with an array and just fill it in instead of having a cache that gets populated as recursions happen. Go back to the picture. Okay? What kind of code would you write to fill in that array right here? Yeah?
Just use a double for loop.
Right, it would just be a double for loop. I mean, look at how I filled it in with the animation. Okay? So we'd have, to set up, we'd have a loop, we'd allocate the array of the right size depending on the length of the strings. Then in the bottom row, I'd write a loop that just fills in the numbers from 0 to 5. Then I'd write a loop that fills in the first column from 0 to 5. And then I write a loop that iterates, lets n iterate in this direction. And m iterate in that direction, or I and j, however you want to do it. And you just fill in this box, this box, this box, and so on, according to these rules. So, to fill in this box, you would look at this one, take the min and add 1. And it's just a doubly nested loop that goes and fills in the array. Just like that. That would be an animation of the algorithm, and that's what it looks like. We create the two-dimensional array table. There we are filling in the bottom row. There we are filling in the left row, left column. And then we have the doubly nested loop. I need an here. They go from 1 up to n. And we've got one of the two cases. Either things are equal. So we do this. We just copy the diagonally adjacent value into table ij. Where they're not equal, in which case we take the min of the 3 elements, add 1. And then when we're all done, there's our answer that we return. So that's another way to do it. So which is best? Fill in the table explicitly, like this, or write the recursive solution and cache things? Yeah?
Typically the table, because it has better locality and doesn't use as many stat frames.
Okay, so we avoid any problem with, if we do it this way, there's no recursion, there's no problem of, with recursion you can end up with blowing the stack if the recursion gets too deep, although there are other ways to deal with that as well. There are exceptions. We'll see cases where the filling in the table version doesn't work as well, isn't as efficient as the recursive version. But typically, for a lot of applications, the table is just going to be more efficient. It's just tighter. It's a little harder to come up with because you've got to understand the problem well enough to figure out how to represent all the values in an array somehow, or in some data structure. And you've got to compute things in the right order, right? You can't start from the upper right and work down. You can't start from the lower right and work in the other direction. You've got to be sure that when you go to fill in an array value, you've already computed it. When you memoize, when you cache a recursive function, you don't have to worry about that. It just works out. Okay? Traditionally, this is what's called dynamic programming. It's setting up a problem we solve in this form, filling in a table. But in terms of programmer effort, the caching method is easier. It's almost like another step to solve this problem. Okay, so let's we'll go to another set of slides, and this is another problem that I got asked after class last time. After you have filled in the table, how do you recover the solution? In other words, okay, it's 3 edits, but which 3 edits? What 3 edits do you apply to Snowy to turn them into Sunny? So if all you want is the number, that's fine. That may be all you want to know. But if you want to know the full details, you've got some more work to do. And the way you do it is, once you've got all those things computed, start up where the answer is, and reconstruct how you computed that number. Okay? So let's just do the following exercise. Why did we write a 3 up there in the upper right-hand corner? Yes?
Because the last letter for the C and
Okay.
the minimum of the options.
Okay, so that we're in a case where the letters agreed in this case. And so we just copied that 3 from the thing diagonally adjacent to it using this rule right here. So if that doesn't correspond, that didn't require an edit operation because the characters are the same. So that's where we start. We copy that number from there. And that, no edit required for that. Now, why did we write a 3, that new 3? Why did we write that 3 right there? Where did the 3 come from? This one right here. Yeah?
Just adding 1 to the minimum of the one we had.
Okay, we took the minimum of these 3, which was 2, and added 1. So essentially, each of these numbers corresponds to a different kind of edit. Okay? So we're going to pick one. What we're basically doing is tracing our way back to the beginning. And we took them in, and there are two that have a 2. Let's just assume that, let's just pick this arbitrarily as where we came from. Okay? That corresponds to a deletion. So if you go back to where we came up with these three operations, one corresponded to deleting a character from R, one corresponded to inserting a character into R, and another corresponded to replacing a character. So each of these cases corresponds to some kind of edit. So what we just did was we figured, okay, when we were figuring out what that 3 was, we took the 2 and added 1 to it. So we were essentially doing one edit. That one is an edit. So we figured out what the first edit to do is. Now, why do we write the 2 there? Why do we write this 2 right here? Again, we took the min of these 3 things. That was the min, and we added 1 to it. And that one is this one right here. That's this case right there. And what case was that? How do we derive that case? What kind of edit led to that? Hard to remember. That was a replacement. Right? Now, why do we write this 1 right here? Okay? Because we took them in, it was of these 3, it was a 1, we added 1. So let's say we took this 1 and added 1 to it. Well, I guess I didn't do that. Let's say we took this 1 and added 1 to that. That's our third edit operation, so that will be not a delete, not a replace, but an insert. Oh, I take it back. That was a yellow one, so we just copied up, so that's no edit. Sorry about that. Yeah. Let me go back here. We wrote this one here. That's a yellow box, so the character in and in agree. So we just copied this one up, so there was no edit involved there. Okay. What about here? Why do we write a 1 right here? Because of 0 plus 1. And that is what corresponds to the insert operation. And then finally, we wrote this 0 here because there was a 0 there. So we started at the beginning and worked our way back, started at the end, at our answer, or worked our way back to the beginning, reconstructing why we made each choice. And you can see this works now. Let's try it out. So if we have snowy and sunny, so it says delete R3, so 0, 1, 2, 3, so delete the W, that gives you SNOY. Replace R2 with S3, which would make that into an N, and then you'd have SNNY, and then insert at S1 at R1, so we take this U and stick it in, and we have SUNNY. So we can reconstruct the decisions we made, figure out the answer. Now, we had some arbitrary choices. Like right here, I chose to backtrack to that spot. I could have backtracked to that spot. I could have said, what I did was I said, okay, we took this 2 and added 1 to it. I could have said, we took this 2 and added 1 to it. So what would happen if I took different route back to the beginning? Would I get a wrong sequence of edits?
No.
What would I get?
Different sequence.
I would get a different sequence of 3 edits that still work. So there's multiple solutions, multiple ways to do it with 3 edits. All right? Yeah.
When you're deciding what to put in the top right one,
Mm-hmm.
that's the case where Rn minus 1 equals Sn minus 1?
Yeah.
So can you show what Rn minus 1 is and what Sn minus 1 is?
Okay. Well, this is R right here. And this is S right there. So in this case, R and N and M are 5. So this string sub 4, 5 minus 1 is what?
I'm not sure I understand.
Okay. Snowy is a string of length 5. That's R. Sunny is a string of length 5. That's S. Okay? Upper right hand corner is at index 5, 5. So n is 5, m is 5. You subtract 1 from n, you subtract 1 from 5, you get 4 and 4. And this snowy sub 4 is right here. And sunny sub 4 is up there. They're sort of lined up along with these indexes. These indexes belong to the array up there. So it's a little misleading to, looks like maybe this is index 5, but this is index 4 of the string. Yes?
Is there no way that you can get the path as you're constructing it?
All right, okay, good idea. Instead of going back and reconstructing it, why not, when we write the 0 here, just remember, well, I guess there's nothing to remember there, but when we write the 1 right here, just remember we wrote the 1 there because insert. Okay, so associate with each square here, not just a number, but the list of edits that got you to that point. What do you think of that? Would that work? So that when you're done, you just got the list of edits computed. Question? Yeah?
It's a way larger space required.
Right, it takes a lot more space now. Because before, we just had to store a single integer in each of these boxes. This way, it's an integer plus a list. And the list can be up to n long. Number of edits can be up to n edits. And so you end up with way more space to consume. Because you're essentially, you're storing it not just for the bolded numbers, you're storing it for every single box you compute. So it makes it a lot less space efficient. Yeah?
When we're going back over the edits to reconstruct the solution, do we assume that the indices change, like after delete? Do we assume that the index just is blank, or do we assume that it's actually
Well,
everything?
because you're working, it would be confusing if you were heading in that direction.
Right.
But the way this is constructed, when you read it down, when you delete index 3, that changes this thing to the index 4.
Okay.
But you never refer back to that index. The index is getting smaller as you go down. So you don't want to read them up or it doesn't work. So we're going reverse. All right, so that's nice. What if we don't have a table? What if we use the caching method? Are we out of luck? Can we reconstruct a solution from a cache?
Doesn't hold all the same information.
Yeah, it holds exactly the same information. It's just organized in a hash table instead of in an array, but it still has every single one of these key to pairs of indices, so you do exactly the same trick. Now, let me show you potential efficiency. Suppose you did not care about reconstructing the solution, you just wanted the number. How can you do this in less space? So this takes two strings of length n, it's going to take n squared space. Yeah.
Do you actually have to fill in the entire array, or can you only fill in the areas that are needed each time you try to compute
Well,
something towards the upper right?
it's a little hard. It'd be nice if we only had to fill in the ones that matter. But it's hard to tell which ones are going to matter if you've done it. There's a simpler way we could save space. Yeah.
Is it possible to know that you're either going to have a no edit or an add one function, so you could just kind of do like a min trail?
Well, I mean, you could. So look ahead and see these yellow things coming up. You might know there's no need to compute either of these. Well, except this might that could depend on it. That's not what I had in mind. Yeah.
Since you're only editing one line at a time, could you just have a few one-dimensional arrays?
Okay. That's it. Think about when you're computing this last row up here. What values in the array does this row depend on?
The ones below it.
Just the ones below it. Once you filled in, say, this row here, row 4, these first rows here, 0 through 3, don't matter at all. You never look at them again, right? You fill in this row, then you fill in this row, then you could throw the first row away. You don't need it anymore. So you could get by with just 2 one-dimensional arrays. The one one array is the one that you're currently computing, and one row is the row you previously computed. Then when you're done, the row you just computed becomes the previous row, and now you compute a new row. So you end up just needing linear space in that case. What about with the recursion, though, with the caching? There's no easy way to do that. And so this is a case where if you, if all you care about is that number in the upper right-hand corner, with the table-driven method, you can do it in linear space. With the recursive caching method, it's going to pick quadratic space. So the table is a clear winner in this case.